fell like right above her head. Like I know it was like right here. But maybe she moved.
Yeah, and one time I just set the ball above me and then she spiked it immediately and I fell over.
Me?
Yeah.
Yeah, I did not do that one on purpose.
No, well,
I meant for it to go down more, but it didn't work.
I'm coloring. You guys want to know?
I don't think I'm going to go to work tonight.
Okay,
It got really quiet.
today, you'll need a book. We'll be on like page. 98. You'll need these diagrams. Cut them out. Take it into your notebook.
I'm coloring a parrot. Do you like it? Hold on, I can't find the other 7.
Oh, it's recording.
what are we doing with this?
Cut these 4 out and take them in your notebook in that order that they are. So the red circles, the colorful ones, the tan ones, and then the tops. Yeah, 1, 2, 3, 4.
One on each page or all on?
1 on each page.
In like,
Why do you do?
because I left mine in class. And then I forgot about it. Let me just do
They were talking about like where they were born and stuff. And then there's one girl like me, she goes, my brother was born in a crash. Okay. You're first grader. Why do you know that? Also, I don't care. Real. Real weird. Funny but weird.
That's my profile name on Craigslist.
And making a mix of me.
4453.
I have too much.
You would have watched some of it.
I think it's because I actually.
Yeah, I know. Well, then she just made me mad, and I was like, whatever. Who? Yeah. She goes, I don't get in trouble, and then I'll cry. I was like, you're gonna make me cry right now because this is literally
Real.
Yeah. And we don't have our phone. Well, what do we do with the else phone?
My thing is, like most teachers are on their phone. So why is it so
Well, yeah, she was on her phone, and then the 2 other girls were on their phone.
What?
It is really close.
I know, like smaller stuff.
Do I? Oh!
Do you think we only need like one for each of these? Or do I just like?
One on each page? What was the order it went in?
Remember that one? Then that one, then that one.
Can I have?
My finger currently up. But
What order do we do?
1, 2.
I'm dying on these. Bless you. Bless you. Thank you. You okay?
Me too, Mr. Scribner. That's how I feel.
Me too.
Me as well.
Can I see those tapes with you?
I'm gonna just wait for them to finish these.
Okay. So,
Wait for them to look more. These ships are fun.
But I forwarded it to an email. She said, sure, that works for me.
Yeah, but
I don't know why I was doing this. What? Do you know why I'm maybe I should.
Because if a teacher requests a student or a group of
Okay, but
students,
we asked the
then
transfer. She said,
they're in there, then people may need to be moved out, shuffled, you know, put in the
which way does
column.
this go? Does it go
But
this
you
way?
can email, if you request, you can email Mr. Hoffman and say,
I don't think it matters.
and the teacher, I would request to be in this ER at this,
Well, we did that
for this next round.
because me and Bryn were in Constance yard until like, what, Tuesday? We had switched us. I'm not filling any of my, I'm not filling any of my online classes. Bryn doesn't even have online classes.
well, and. Well, did you just want the PE stuff and move the rounds? Yeah, it's like
Well, we tried to put up today, but you know, I needed to get an email. This morning, she was like, no, you have to,
Good, so did you email and then so tomorrow?
Well, I emailed asking to change it. I'll email tomorrow morning, asking for
Good
change.
one, Josh.
For tomorrow's day. Terry, I emailed.
I just
We
say,
should
and then-
be- We
and
should
then-
be transferred by.
Include Mr. Gregory on it. Just
Yeah.
be like, can I be permanently moved back
Well,
into?
we emailed Mr. Coleman, Mr. Hoffman.
You have to see Gregory in there because he's the one that switches in.
Oh, tomorrow I have a.
Because that's not. Wait, I'm gonna put this one. There won't be any more tomorrow.
Are we supposed to do one a page?
Yeah.
Yeah. I did two on these because they're small.
Probably
Probably. It's not like I write things. I write things.
Yeah. You could.
I do and I don't. Mine's like a happy medium.
I mean, it's not like.
It's not bad.
It depends on the day.
I just want to keep coloring.
I just want to go home.
Me too, my
Okay, but I should have home like, I should get out earlier because I have a 30-minute drive home.
This is a quantum, so do I.
Yeah, so for this section in your notes, call it quantum modeling.
Like on this one, quantum.
Yeah, that on the beginning of the first
Well,
one.
normally she
red
texts
line,
us, right,
quantum mod.
that,
Oh, don't come in if.
yeah. Well, one time we came into work for 40 minutes and she's like, oh, you can go home now. Or,
Okay, bye.
okay, but that's a waste of freaking gas.
You're gonna get a buck 40 minutes to get paid hourly.
Right.
Less than
I'm just gonna take them separately.
Well,
This one?
I just cut these ones super small, so.
Is this one too? That one's Louis. No! Oh, it's all gone. The carbonation's everywhere.
Where did you get this from?
Right behind you.
Oh, perfect.
It's also-
Hey.
I like to write a little bigger. Yeah.
Who is she? Abby, what'd you get on your, practice?
I don't know, I don't think she's very good.
They're in, cause our classes is in, and you're a day before.
Okay, so we're gonna start
I got
off
an 86.
reviewing a little bit of what we've talked about before with waves,
What'd you get?
and then going into this new reading on quantum model and how we change the Bohr model into the quantum model. So, first of all, Ashley. First of all, if we were to describe what an element looks like let's say hydrogen, if we were to describe what hydrogen looks like using the Bohr model, how would we describe its structure?
Where do you like draw a circle?
I would draw a circle.
And then you would wait, what element did you say?
Hydrogen.
And then you put an H.
Okay, so I'm gonna draw a
You don't have
circle.
to do that.
And I'm gonna draw an H. Okay, good.
And then-
And what does that represent?
Where are we drawing this?
The nucleus.
And then you write like the circles around it, and that's where you put the
Electrons.
Okay, it's hydrogen. How many electrons?
one.
One, it only has one.
So you just put it on the outside. Like that.
So I just draw another circle.
Yeah. and
Well,
then-
maybe the other class told me I needed to do it this way.
This is how we did it last year.
Yeah.
And then don't you put your protons?
And then I have protons, which are positive, and neutrons, which are neutral, and I have electrons, which is negative. Right, okay, good. That would be a good Bohr model representation of what hydrogen looks like. One proton, one electron, depending on the isotope, we may have a neutron or not. All right. How would we describe lithium, or helium? Helium's number 2. How would we describe helium?
Same thing except two.
Same thing, so circle, it's lithium,
Lithium or helium?
2 protons, how many electrons?
Yeah, I don't know.
Oh, I'm sorry.
I said,
Why
what are
not-
we doing lithium
I'm
or
really
helium?
wanting to do lithium, I don't know why. We're doing helium,
Um,
with 2
ew.
protons,
Yeah.
Ew.
and how many electrons?
Ew.
2.
Warm.
So that might be a Bohr model representation of helium,
Yes.
okay?
That looks right.
All right, lithium,
3,
3 electrons. Now this is the question, does the Bohr model tell us how many electrons are in that
Per ring?
ring?
doesn't it tell us how many rings you should have?
It
based
does
on
tell
which
us how many
row it's
rings, and what did those rings represent?
The levels?
in? Which row it's
The excited state or
Yeah,
the
the excited state. So those rings represented 1, 2, 3, 4, 5, 6, 7, which was infinity.
Yeah.
Okay, so those rings represented excited states, which electrons could be there, but how many?
For each one.
Wait, for which element?
It depends on the element.
We don't know. Like the Bohr model never said. This is where, right, when people took the next step to describe what the atom would look like using the Bohr model, how many electrons? And then, okay, electrons could be there. We know that there's a space there for electrons because they're moving there and moving back into these excited states, back to the ground state. But how many? There wasn't really a clear conclusion as to how many electrons there were per each level. Okay? And so people started to look at the electron differently to try to figure out, okay, if it doesn't work this way, then we got to look at it in a different way to figure that out. Okay? And that's where we jump back to this, where we first started when we were talking about waves. Bohr's work really treated the electron as a particle. The electron is here, in this position, and it's in a ring. If I were to ask you, like, where do I put the electron? A good answer might be on the circle, right? Right there, on the circle. Right, so it has a position. When it's excited, it's at a higher position. Right? We could also describe, speed. Wow, this is good. Turn back to page. Where were we at? Where we started? Turn back to.
I know we had red 93. Well, you're going way back.
Yeah, try to find a
I
picture.
like that the back because it's still full of air.
Oh, 71. Turn back to 71.
71.
So up to this point, there really is this strong idea that the electrons are particles. And this experiment is like what we go back to. There's the cathode ray tube, there's the paddle wheel, right? If you throw a baseball at a little paddle wheel, is the paddle wheel going to move?
Yeah. It's the baseball.
Because the baseball has mass, it has velocity, it's going to apply force to the paddle wheel, which is gonna cause the paddle wheel to move, right? All those Newton's laws things. And so the electron's a particle. The problem is, when we look at the electron as a particle, it doesn't allow us to apply it to elements with more than one electron. So we gotta look at it differently. The important thing here is that all of this work showed that there was a relationship between the electron and the photon. Okay?
Who's that? Going to the side of speed, going back to it, it's the photon of light.
Right. Well, what's light? Is it a particle?
Yeah. No. What is it?
No, it's a wave. Traditionally, light was thought of as a wave. But then Einstein was like,
What about it?
maybe it could be a particle. And you've got this wave-particle duality thing. Okay, well, if the electron is a particle, maybe also the electron could be a wave.
Sure. But if the electron.
Okay, so if that's true, then we have to think about it as a wave, which means it's moving in all directions. It has no mass, no volume. Its position is temporary because it's always moving. Okay, and so if it's always moving, is it moving at the same speed? Can it change its speed? It doesn't have acceleration. So we have to think about the electron differently if we're going to think of it as a wave. But it allows us to think about it differently, and this is kind of the key thing. So here's what we need to think about. All right, here's the analogy, and it works. Here's my best airplane.
Ah, good job.
Okay, you look up in the sky, the airplane is flying. Does it have a position?
Right now it does, but it's always going to move.
Right, it's moving, but I can measure it, I can see it, and I can measure its position, it's moving.
Because
Yeah.
it's big enough, yeah.
And from those, I can get a speed.
Yeah.
Okay, perfect. The plane flies behind a cloud.
Yeah.
Okay.
Okay.
Your task is to design a rocket launching system to shoot down the plane. Okay?
What?
While the plane is here and while you're tracking it and while you're measuring it, how easy is it for you to shoot it down?
It's easy, but they can also see you blowing the ground.
All right.
And I'm playing it.
But once the plane flies behind the cloud, what are you going to have to consider?
How fast it's going.
Okay, we're going to have to consider its speed.
How far it goes. Up and down.
Up, could, may, up and down.
The position. Amplitude.
Because once it passes behind the cloud, where is it?
In the same
Oh,
position.
Sherman's equation or whatever. You don't know until you see it.
Yeah, it's in the cloud. The cloud has a size.
It's really fun.
So, if we're going to try to shoot the plane down, we're going to measure some things, but then we're going to have to assume some things.
You could wait until at the very edge of the cloud where it's going to be leaving and just aim towards where.
Well, that's going to be an assumption. We're going to assume
It's going to come back out the other.
that we're going to, this whole thing in here, that's all going to be an assumption. Because we can't see it, we can't measure it, we can't see it to measure it. Okay? So that's all going to be assumption. So we're going to assume, I mean, are we rightly assuming?
Yeah.
We are rightly assuming because we have some information, and based on some experience, we're pretty sure that it's going to continue in a straight line and it's going to come up here.
We've done this
But
before.
all of that, we're going to assume. Okay? But we need to assume that for our missile
Thing.
shooter down system
Amen.
to work. Okay? So, we're tracking, we're measuring, it goes behind the cloud, we shoot. Where is the computer going to tell us to shoot? Right there, boom. It's going to tell us to shoot right there, right? It's going to take in this information and it's going to say, shoot right there.
At this time.
Well, you have to know what speed you're.
Right, so that we put that into the computer. We put that in the computer, we put wind in the computer, we put the rays of the sunlight and the UV and the dog barking. We put all that in the computer, and the computer told us to shoot right there.
Use the computer and shoot at the cloud.
Okay, are we gonna hit the plane?
No.
Depends on what.
It depends on how fast.
Entire-
Oh, depends. That's a good word. It depends.
Depends on how fast the.
Depends. Okay. All right. Shh.
Don't think of it.
Take
No.
two. Take two.
The plane went
Okay.
over the clouds.
Take two. We're in a new situation. Same plane, same cloud, but we're gonna shoot again. Okay. Now different speed, maybe different position, different wind conditions. Now it's raining, and the plane is a 747 instead of a 737. And we put all that in the computer, and it tells us to shoot right here.
That doesn't make sense.
We're trying to shoot the plane
That's
down.
the American spirit.
We're trying to shoot the plane down. Try and shoot.
What if the plane goes over the clouds?
Or under clouds.
No. See? We're gonna assume. Now, that's a good question. Would the computer ever tell us to shoot right here?
No, because it doesn't take that into account when it's calculating the spin.
Okay, but given all of the things that it depends on, might it?
Maybe, depending on the weather and everything.
Maybe. Okay, maybe. But
Maybe
what are
they
the
realize it's
chances? What are the chances that it would tell us to shoot
At the
here?
very bottom.
If they shot it once and it started falling, but it was still flying.
Would there be a chance that it would tell us?
Well, maybe.
So if we did this a million times,
But it's like not as high of a chance as the other chances. Oh yeah.
yes.
Boom.
It's not as high, but if given all of the possibilities, is there one chance in a million?
Yeah.
Yeah. Okay. But the closer I get to the cloud,
The higher the chance.
and the closer I get to the thing that we know as people, right? The plane. The closer I get to that line,
Higher chance you hit it.
More
Okay.
accurate.
okay, yeah. All right. So, we're gonna kind of use this scenario and relate it to the electron. Because if the electron is a wave and it's always moving, where is it?
On the path.
Ahead of where it was before.
Or
Okay, but-
behind where it was.
Okay, when we talked about waves initially, like where is my voice?
Everywhere.
Where's your voice? Where is the light?
Everywhere.
Okay? But it can't be everywhere, can
Everywhere
it?
that we
It's in a position.
So it can be everywhere, but it can be everywhere.
Everywhere and nowhere at the same time.
And we know that
It's somewhere
based on what Bohr was doing,
It depends.
it does depend, and some things are gonna have to happen where it's everywhere, but it's constrained to
a space.
a space,
Yes.
okay?
Now what if we observe?
Okay, all right. So, if we, given enough time, if we did this 100 million times and we just filled this with x's, all of the x's would take the shape of what?
The plane.
Where the plane
Would be.
Could be.
Is
could
assumed.
be.
Yeah.
Okay, so if we do this enough, it's gonna tell us where the plane could,
We miss
be.
it every time.
right? It's okay, right? It's really not about shooting the plane down. It's really about deciding where the plane could be. All right,
To get that plane.
so let's read, and well, some people started thinking about this. Okay, if the electron is a wave, then we need to think about where it could be, and not Bohr's model, which was really trying to tell us exactly where it was.
Yes.
Okay, so we're gonna start reading on 99 because that first part really is just talking about waves and really is getting to this plane shooting down idea. So, River, do you want to start us off on the top of page 99, Heisenberg uncertainty principle?
Sure. The idea of electrons having a dual wave particle nature troubles scientists. If electrons are both particles and waves, then where are they in the atom? To answer this question, it is important to consider a proposal first made in 1927 by the German theoretical physicist Werner Heisenberg. Heisenberg's idea involved the detection of electrons. Electrons are detected by their interaction with photons. Because photons have about the same energy as electrons, any attempt to locate a specific electron with a photon knocks the electron off its course. As a result, there is always a basic uncertainty in trying to locate an electron. The Heisenberg uncertainty principle states that it is impossible to determine simultaneously both the position and velocity of an electron or any other particle. Although it was difficult for scientists to accept this fact at the time, it was proven to be one of the fundamental principles of our present understanding of light and matter.
Okay. Right there in the middle of that paragraph. As a result, there is always a uncertainty in trying to locate the electron. Alright? We're going to shoot at the cloud. We're going to assume some things, but we're uncertain if we're going to hit it or not. Okay? Huh?
We're lucky we'll get it.
Right, if all of our measurements are good, then. Alright. So Heisenberg states his principle that if we treat an electron like this, then we can't know where it's at and how fast it's going at the same time. We can't know that at the same time.
That sucks.
Okay? And so one of them we have to assume. We're going to measure one and we're going to know. The other one we're going to have to assume. Okay?
Does it depend which one we assume?
No, it doesn't matter. If we measure the velocity, then we assume the position. If we measure the position, then we assume the velocity. Okay. And then, in so doing, we're going to shoot, and it's going to tell us shoot there.
Sure.
And depending on our assumptions, right? Our assumptions are going to constrain things to a shape, to a cloud, to a space, and okay. All right. So Heisenberg's like, see, if we do this, we're gonna have to consider this. So then Schrodinger comes along and is like, okay, sure, you can do that.
Sure.
And so, what are the chances? Can you mathematically do a chance?
Yeah.
How do you do chance? 50-50, yeah, that's a chance. That's 1/2, 50-50. Five, or no, that's, it's a ratio, probability, chance, right?
I don't know.
If I measured all my things and did all my assumptions, could I calculate some kind of a chance that when I shoot at the place it tells me to shoot, I'm going to hit it?
Sure could.
I could, 1 in a million, right? 1 in 10,000, 1 in 100,000, whatever. It's going to give me a chance, okay? But we already said it. When we get closer to where it's really supposed to be, what are the chances? Like 1 in 2, like we'll hit it every other time. Okay, so Schrodinger's like, okay, we'll just do this. We'll just calculate all these probabilities like 100 million times, right? And we'll just see what comes up. So, Ashland S. Next year in 1926. In 1926.
Okay, and then 26, the Austrian physicist Schrödinger used the hypothesis that electrons have a dual wave particle nature to develop an equation that gives electrons and atoms of waves. Unlike Bohr's theory, which assumed quantization as a fact, quantization of electron energies was assumed
It was a natural outcome.
was a natural outcome of Schrödinger's equation. Only waves of specific energies and therefore frequencies provided solutions to the equation. Together with the Heisenberg uncertainty principle, the Schrödinger wave equation laid the foundation for modern quantum theory. Quantum theory describes mathematically the wave properties of electrons and other very small particles.
Okay. So right in there, only waves of specific energies. Last time we looked at the spectrums. Hydrogen, it had like a red line, teal line, purple line, right? That color,
What's the spectrum?
there was an energy associated with that color.
Yeah.
And So that energy, when Schrodinger used that energy as an input, he got an answer. Other energies from other things, no answer. Okay? And so that, we can think about looking at those colors, and so the energy from that color, and Bohr was right in concluding that, that energy corresponded to a particular location away from the nucleus, some excited state. We're just going to look at it differently. Instead of this, we're going to look at it this way. Okay? All right. So, at the end of Schrodinger's work, he proposes that there are four principles that we can use to describe the structure of the atom, okay, locating where the electrons are, and when we have 2 and 3 and 4 and 5 electrons, where are they at? How are they arranged? Okay? And so that's going to be Ashland W on 101 in the Bohr atomic model.
Oh, in the Bohr atomic model, electrons with increasing energy occupy orbits further and further from the nucleus. According to the Schrodinger equation, electrons in atomic orbitals also have quantized energies. When an electron's energy level is not permanently boosted of an orbit, that is indicated by solving the Schrodinger equation.
Blank.
In order to completely describe orbitals, scientists use quantum numbers. Quantum numbers specify the properties of atomic orbitals and the properties of electrons in orbitals. The first three quantum numbers result from solutions to the Schrodinger equation. They indicate the main energy level, the shape, and the orientation of an orbital. The spin quantum number describes a fundamental state of the electron that occupies the orbital. As you read the following descriptions of the quantum numbers, refer to the appropriate columns in table 4.2 on page 104.
Okay, so this is where we're going to get into your diagrams. Okay. And so when we look at these, the first three are going to be what Schrodinger figured out from calculating these probabilities. Okay. And what's interesting is as the energy of the photon increases, right, so as the color changed, it gave different shapes, different spaces. Okay? And so they're not all sphere. The most basic one, for all electrons that are close to the nucleus, the shape is a sphere.
Circle. Is that why we use this?
Yeah. Which I think is, I don't know if Bohr really thought that way or not, because we call it like the planetary model.
Good for him.
Okay.
Oh,
So, Earth is going around the sun, but the problem is, like, what is our path around the sun? Round, like a circle.
Yeah.
Are we like,
But not all planets
Not like
are
Pluto.
like that.
are we all over like a sphere? No, we're not. Our orbit is not like a sphere. Like we
spin while we
cannot
go
be
to the sun.
anywhere in the sphere around the sun. We are in a plane. Like we're two-dimensional. So we basically are always looking at the same spot on the sun. Are we ever going to look at the top of the sun?
No.
No, because our orbit doesn't take us over the top of the sun to look down
How
on.
cool would that be if there's
We will always be looking at the side of the sun, if you want to think about it that way. Okay. But, so I don't know if Bohr thought that or not, but the Schrodinger equation clarified that. The electron can be looking at the side of the nucleus,
but it'll never
but it can also look at the top. So it can be It can be, so the Jimmy Neutron model.
Okay. I've never watched that. I know what it is. It's the one you watch. Oh, with like the looks like a pentagon stuff inside of it.
No, it's a really big head.
Well, I know it's Jimmy Neutron is, but I'm talking about the model. But, like the one that looks like a pentagon inside of it.
Yeah, where the electron can be around the side, but also over the top and at an angle.
Why do they call it the Jimmy Neutron?
Because that's how I think of it.
Oh, okay.
What's it actually?
Which is not, this is not the planetary model, right? Because our planets do not orbit like this. Our planets are all kind of in the same-ish, always looking at the side of the sun.
Yeah.
Okay? There aren't any planets that orbit over us and under
You know how
us.
cool that'd be though?
That would be weird. Okay.
I was thinking the Big Bang Theory.
Yeah, that's another one. Okay. So Schrodinger was like, yep, it's a sphere, and so that electron can be anywhere in that sphere, not just in a pathway. All right. You could jot that down, but we're gonna describe it, and so there are 4 numbers. Number 1 is the red gobstopper.
Oh, wait, what? The little tiny little
Yep, that's the target looking. All right, so the principal quantum number, it's going to describe the distance from the nucleus. And so you can see it has these concentric rings, each one a little bit farther away from the nucleus, kind of like a gobstopper. And we have 7. There's 1 through 7.
Wait, what did you say? It describes.
Describes the distance from the nucleus. And there are 7, 1 through 7. So that it's a number, 1 through 7. One being the closest to the nucleus, 7 being the farthest away from the nucleus. This was the one thing that agreed with the Bohr model.
Oh, okay.
How many states were there? Besides the ground state and the excited state, you add all those up, how many states were there that the electron could be? 7. Ground state, 6 excited states. Okay. And Schrodinger's model showed the same thing, that there were 7 distances that the electron could be from the nucleus. Okay. Next, angular momentum.
Is that on the right one?
So now we're to the sphere and then these linear, like ice cream cone, like a mirrored ice cream cone. So, to angular momentum. Okay. Angular momentum describes the shape of the space. Angular momentum describes the shape and I'll say cloud because we call it the electron cloud model. Maybe that's where I first pictured it. I mean, if you picture it as a cloud, clouds are not all the same shape.
No.
So angular momentum is going to describe the shape of that. Where does the shape come from? All of the things we measure and trying to shoot, and the higher the probability, the higher the chance, then all of my x's take on a shape. Well, it turns out they're not all spheres. Some of them are spheres, but some of them have they radiate out from the nucleus and kind of form this like It's like a hot air balloon, right? Because it's three-dimensional, so it's like a hot air balloon coming up from the nucleus and down from the nucleus upside down. They're a mirror of each other, right? That's that one. Then the next one is like the hot air balloons, but then it has like a life-saving donut on it, a little inner tube around its nucleus. And then these, then the next one has inner tubes that are above and below that one. Okay? So those are the shapes. So there are 4 different shapes. They are also a number. 0, 1, 2, 3. Write it over here. 0, 1, 2, 3. Okay. So those are the 4 shapes. 0, 1, 2, 3. You could also call them their letter name, which is S, P, D, and M. S, P, D, and F. So, I don't know, when I learned them, I didn't learn them as a number, I learned them as S, P, D, and F.
Or is the S?
But S is 0, P is 1, D is 2, and F is 3. So if you wanted to write that in your notes, you have S, P, D, and F on your diagram, just write 0, 1, 2, 3. And that's the number classification of that shape. 0 shape being spheres, which that makes sense with S. P is the hot air balloons. D is a hot air balloon with an inner tube, and F is a hot air balloon with 2 inner tubes. Okay? That's what the shape of it would be. Like you do all the things and you shoot, and once you get them all shot, it takes that shape.
So what shape would this be considered? A cloud shape?
Well, geometrically, right, it doesn't have a other than a cone. Right, a cone, like it's a cone. But geometrically, it really doesn't have anything. That's the name of the shape.
Or shizzle.
What's that?
Is it or shizzle?
Here is a diagram. So this diagram here is actually the mathematical solution, all the probabilities, and that's what the shapes look like. So, kind of. Okay. But we'll look at them like this. Fascinating. All right. The third number is magnetic number. Okay. 3.
Those are like the tops.
No, these are going to be like this tan one down here with these X's pointing in different directions. Magnetic number. And to think about this one, how does a compass work? Because magnet, think about how a compass works.
It changes them
To the poles.
To the poles, because it's magnetic and it's pointing to the North Pole.
Yeah.
Yep.
It's magnetic.
I guess.
So it's pointing in a direction.
Yeah.
Right? The compass points in a direction
Yeah.
because it's magnetic. So the magnetic number describes the direction orbitals are pointing. Okay. So if you want to look, turn to page 102, and we'll kind of put this diagram together then. On 102, we can see that the s orbital is a sphere. Does a sphere point in a direction? No. So that's number 0. Okay. Well, I should do it this way.
Wait, what's zero?
S orbitals, because S orbitals are spheres, S orbitals are not pointing in a direction, so they have no direction. 0. That's their number. Okay. But if you look at the p orbital, notice that the p orbital, since it's kind of linear, it can be pointing toward you and away from you. Or it can be pointing side to side. Or I'm on page 102 on the bottom on the SP orbital. Yeah, see the p orbital?
Yeah, I see it.
The green one?
Yep.
Yep. See how it's on the y-axis?
Yeah.
But what if it was on the x-axis?
Then it would be this.
Then it would be the same, but it's pointing in a different direction.
They are.
And then z, right? So they're pointing in different directions.
Yeah.
Okay, so p orbitals, p, d, and f, they can point in different directions because they have a different shape. So p orbitals can have, they can point in 3 different
So
directions.
the
X, Y,
only
and Z.
one that can't point in any direction is the S orbital.
Because it's a sphere.
Okay.
P points in 3 directions, X, Y, and Z. D points in 5 directions. And F points in 7 directions. D, one of the directions in D is the inner tube. And 2 of the directions, I think, go back to the two of the directions F are the inner tubes.
No.
This is a.
Are we almost done?
We're close.
This is
Are you ready? You done?
I'm so tired.
Well, it is 4 hours.
I was like really close.
You need to take one of these energy from this show.
Me?
Like the 5-hour energy thing.
I had half a Red Bull today.
Half?
Yeah.
Sounds like you should have the whole thing.
Well, no. You see, because if I have one, then I go and buy like 5 more and then I'll drink them all.
When I drink
Okay.
Red Bulls or Monsters, I can feel this one's in the like, it was like it feels like,
You have height or something from spiders.
oh, I don't know, it's like, you know, the feeling that you get when you need to pop like your finger or something. But I feel that in all my fingers all at the same time, and I can't pop it. It's just like I feel them.
Okay, the last
All the time.
way that we describe the electron is its spin number. Spin, how would we describe spinning?
Around and around.
Speed. Circular.
Like this way versus this way. Are we?
Always
when you're writing.
good.
Can I talk while I'm writing?
Yeah. Like would you just.
Electrons spin either clockwise or counterclockwise. Which is a really interesting like phenomenon, I think, that they are spinning. And how we actually even figured that out is even kind of crazy.
And how did we figure that out?
I'll show you. So they can spin either clockwise or counterclockwise. This is actually really significant because that means we can pair them. Electrons can pair. Can pair. Electrons are what?
Negative.
Negative, which means if 2 of them come together,
Positive.
You can't
Two
put
negatives.
negatives together, but you can put a negative and a positive.
why can't we put 2 negatives like?
Because
They
they.
repel each other.
They push each other away.
Yes, I was.
Okay, so, but interestingly enough, in an orbital, if one is spinning one way and one is spinning the other way, that reduces their repulsion and they can actually be in the same space and not repel each other. Huh. Yeah, is right.
Huh.
How did we figure that out?
That's a great
Delaney
question.
asks.
How does anybody figure anything out?
So, when people were first trying to like really understand and confirm really small particles, you know, whoever read Latin,
I'm trying to find it on.
in the Schrödinger equation it says quantum theory describes mathematically the wave properties of electrons and other very small particles.
Oh,
Well,
they're small, like
oh.
photons and
so there's not just electrons?
protons and neutrons.
No. So what people were discovering as we went into this atomic theory thing, that there were subatomic particles and there's small particles, lots of different
Oh,
particles.
yes.
Very small particles that behave differently
And
than we would expect because they're very small. Okay, so how are we going to observe properties of things that we can't see? Well, at some point, somebody figured out that if you filled a container with dry cleaning fluid and you shot particles through it,
what's in dry cleaning fluid?
chlorine, it's chlorine. So it's this carbon chlorine compound.
Okay.
Oh my gosh, I think I did this for my.
This is a lot like the cloud chamber when you, like with the dry ice that Madeline's doing with her project, where you can see the trails, the tracks.
She's still doing
Like, she's.
She's been doing that for like 10
I know.
years.
So
Girl.
her work this year, she tried to do it in a vacuum chamber. So she built a special one that she could suck all the air out and see if that would improve the performance of the cloud chamber. All right, but so dry cleaning fluids is the same thing, but that's a liquid. Where that one is it's using the condensation vapor from the alcohol. All right, so fill with dry cleaning fluid. It leaves this like microscopic trail of bubbles through the liquid.
God, it's the bubble chamber.
That's why it's called a bubble chamber. All right, so they make this vessel, fill it with liquid, put photosensors all around it. On the inside, looking in at the liquid, shoot particles through it, and voila, we get a photograph of particles going through this liquid. We're not really looking at the particle, we're looking at the path of bubbles that the particle leaves as it travels through them.
Yes.
What do you notice?
It's like spinning.
It's like not straight line.
No, it's a coil.
Well, how do we get a particle like an electron to not travel in a straight line?
You knock it out.
Think baseball.
Yeah, grab it.
Spin it.
Home run.
Spin it.
I don't know.
Right? How does the pitcher throw the curveball? Instead of throwing it in a straight line, right at the end, it puts a little bit of spin on it, and now it's spinning and curves. And the pitcher can either spin it one way or the other way. That's it. There are two directions to spin. Okay? And so paths were either curved up or curved down. So, guess what?
Chicken butt.
Electrons down.
Hooray.
Which means, for Schrödinger's model, that's actually a very useful finding. All right. So, now we have a way to describe this. How many electrons can we fit in this first ground state? Bohr's model, we question mark, but Schrödinger's model, 2. That's it. Okay? Where does, so then lithium has 3 electrons.
It'll have to go.
Where does the third electron go?
The next level. It floats.
The next level up.
Yes.
Beryllium, where does that 4th electron go?
On the second layer.
On the same.
Same with the.
In the second one. Okay, so here we go. Turn to 104. Oh, 104.
You okay?
Okay. Look at the table on 104. I can sense that. All right, that table. Principal quantum number 1. What is the shape of that first energy level? I'm in the blue table.
Sphere.
Sphere, S. Okay, how many, can S be in any orientations? No, it's a
No, it
sphere.
has 0.
That's right, Z.
It doesn't look.
How many electrons can I fit in that space?
Only 2.
2.
Only 2.
Only 2.
Because
Two.
it only has one level.
There's only one level. Okay, good. So now this is important. Hydrogen has how many electrons?
Oh, 1
Where is that one electron?
on the first thing.
Okay,
Yeah.
yes.
Yeah.
But how many electrons can I put in that space?
1 or 6.
2. Okay, 2. All right. So when I go to helium, helium has 2 electrons. Where's the first electron in helium?
The first one.
And then where's the second electron in helium?
Third one. Wait, no, the
First
second.
level still.
Wait, I'm confused. Are they both on the first one?
Yes, and they can both be on the first one because
Electrons compare.
Electrons in pairs.
in the space.
Yeah.
So both of them are in there. Now, the interesting thing is, Schrodinger wouldn't say that. He'd be more like this.
No.
Alright,
Inside
so
it?
those
They're in
electrons
the
are
space.
they're just there. They're in that space.
Oh, yeah,
No,
there.
no, I don't like that one. I like the other one.
Okay. So now now that we have those 2 electrons, can we put any more in the first energy level, in the first principal
No.
quantum?
No.
No.
Only 2
So we go to lithium. Where does that third electron in lithium go?
In the second ring.
In the second ring. Okay. What sublevel?
Isn't it?
S?
Wait. SP. It says P.
Well, I know it says P,
S
but
and P.
S is the lower
It's
energy.
S
So
and P.
well, it's S and P, but it's going to be an S first.
Yes.
And so when you look, okay, so look at 4. It goes S, P, D, and F.
It's an
S has to be first.
That's an S and then it's an
And then a P.
and then a P.
And then if it needs a D, and then F.
Yes.
Finally.
So
So
it's like expand, like the
Yes.
like the rings on a tree trunk from the middle.
I'm confused. On what kind of 6?
where does the third electron go?
In
In the second energy, but in the S shape.
The S
Or in the second energy, but the S shape.
How do you know what shape it's gonna be?
I know what shape it's going to be because we've calculated the energy, and that energy corresponds to a shape that looks like that. Okay?
So we don't know just by looking at like the hormone.
Yes, and I'll show you the connection. Okay. Now, beryllium has 4 electrons. Where does the third and fourth electrons go? Second ring, but
Still an S.
S. Okay. And how many electrons can S hold?
2.
4?
It can only hold 2.
Wait, but is the first ring an S2?
Yep. First ring is S2.
So the first 2 rings are both S?
There is a ring at every level. There's a ring at every level. So
First ring and second ring are both S.
S. And when we get to 3,
Oh,
it's going to be an S. We get to 4, it's going to be an S. It's going to start
When
with
does
S.
it change?
And we don't want it to change. Because we
So
like
every ring
a
is an
pattern.
S?
Okay,
Okay?
got it.
Okay? So now beryllium has 4 electrons. The first 2 are here. The second 2 are also in an S, but they're farther away. Okay? Now boron. The first 4 electrons, 2 in S,
And then the 5th one's on the 3rd.
but
It's
now I start into what? Now I can actually go into the P.
yeah.
And so how many electrons are going to be in that P space?
6.
Well, I can fit 6, but it's boron, so how many? Just 1. I only need 1. Okay? Okay. I'm gonna ask you this question, I want you to think about it.
As you
So, we've talked about where would lithium's third electron be? Okay, good. Which element would have its last electron in the fourth
Oh.
energy? In the fourth principal level.
Yeah.
So oxygen's last electron
Yeah.
is gonna be in the fourth level.
So would nitrogen.
Yeah.
Nitrogen?
I thought nitrogen's first electron.
Would it be nitrogen and oxygen? No?
I don't know, I'm giving up, I don't know.
Because if
That's my
there's
guess.
two level, there'll be two of nitrogen.
How many electrons can fit in total in the second level?
Two.
Three.
4, 7,
No,
6.
no, hey guys, don't guess, look.
6.
8.
8.
What? I thought it was.
How many total?
So P and S is 8.
Yeah, P and S together.
Germanium.
Bryn thinks germanium. Why?
Because it's 32. It's 32. And you can fit 32 into the fourth one.
Oh, maybe I jumped ahead. I should go third. You're right. Let's go back. Let's back up. Whose last electron would be in the third level? There we go.
The third level? Argon.
Argon? Why? Why argon?
Because it would be argon. Because there's 18. Same with chlorine.
Okay.
18. It would fill the second level, but there's 7.
Okay, let's listen. So Bryn says
Wait.
argon because argon has 18.
No, it would be fluorine.
Okay, wait. Argon has 18.
Okay, wait. Are
And
we
so-
talking
and
about
so-
the fourth ring or the fourth?
Third.
Third ring.
Okay. So
So how is it argon?
do you see argon being number 18?
Because 18 can fit on
Sorry.
Yeah.
Okay.
So what does that
Argon's not.
tell you?
It has 3 rings.
Oh yeah.
Like looking at our
because
little
isn't
chart
the
here,
ring
what does that tell
different
you
based-
about
argon.
that level? Can we put any more electrons in that level?
No.
No. So then, where does the next electron go?
The fourth.
Wait.
So
I don't know
potassium
what's
would be
going
filling
on.
their last electron.
So potassium would be starting the next level.
Yeah, the different rows determine how many rings you have, but whatever element is in that row. Like, if you're doing, I can't see.
She's like in the
Well,
zone.
that's
But then
4
you get to the
rings, because it's
transition
in the
phase.
4th row.
I think it's freaky.
Yeah, okay, I got it.
There you go.
Okay, so good. You guys see that?
Yeah. But what about the transition rails? It's weird.
Talking about
All right.
Oh, we're talking about potassium.
There's a lot that
was just said all at once.
I know.
I knew this before.
My brain
Yeah, and you
is
probably,
freshman.
if you remember it from Beans, you probably will remember. Okay.
Use.
Where does hydrogen's first electron go?
In the first level.
First level.
1.
S.
So principal number 1.
Yeah.
S.
1s. Oh, you want us to
1s.
remember it?
All right.
I
So
thought
now
zero
look at where hydrogen
Yes.
only for the shape. Well, you're right. 0 is S. But
0. So is 1.
how close? So we can say 1s because it's the first principal number.
Oh.
When does it
But
start
an
changing
S
from
shape.
the S to the P?
Okay, what
Oh,
like 2s.
and then 2s and 3s of course.
Until it gets to 7s, and then after 7s, it goes to 1p.
No, because at 7s there's nothing because 7 is.
Infinity.
6s. I don't know.
All right. So, but okay. So look at the periodic table. Look where hydrogen's at. Okay. Now it jumps over to helium with 2 electrons.
Yes.
Okay. Where are those 2 electrons at? In S. Okay.
And 1.
Now that S is full. So in order to add any more electrons, I have to add another principal number.
So,
So I have to go to 2.
do the, what are they called?
So I start 2s. Okay, so where does
Helium.
lithium's, where
Do
does
the
lithium
periods
stand?
on the periodic table go with the
Yeah. It also shows you S block, P block, D block, F.
Good, yes, some periodic tables do, some periodic tables don't, but yes, that's right. Okay, so lithium's third electron goes in the second S. Okay,
Yes.
now, beryllium has another electron, where does it go?
The second.
The second electron in that S. Okay, can we put any more in that S
No,
space?
you have
So we have
the
to
third S.
add another shape, we have to add another
Oh,
space.
one
P, but not one P
Three
because we're
P.
not in the first quantum
Just
number,
P.
we're in two, we're in the second quantum number, so we call it 2P. Okay?
So it's on.
And how many electrons can be in P? Well, we gotta look. P has 3 directions, each can hold a pair,
So 6.
so 6. Does that match up?
Oh my gosh. That is crazy.
So P has 3 sublevels, so 6.
Yeah.
So together, that S shape and those 3 P shapes together can hold how many total electrons? 8. What element has 10 electrons? Neon. Neon. So after neon, with 10 electrons, we don't have any more room in the first quantum number or the second quantum number or the second principle. So we have to go to the third principle.
For sodium.
And where are we at? Sodium. Starting in the third principle. Okay? And then, so where's sodium's electrons? It's the first electron in the 3s. And then we go 3s and then another electron. But then notice we jump over to aluminum.
Oh.
Oh, and then Sean says 3p. Because like boron started filling p electrons. So aluminum must start filling p electrons? Yes. So then gallium also must be starting to fill
Yes.
p electrons, and indium and thallium.
Yeah.
And
Oh. So coming back over here, lithium starts filling s electrons. Sodium starts filling s electrons.
Yeah.
Potassium,
Oh, I see it.
rubidium, cesium.
cesium
What do we call everybody in group 1?
in group
Yes.
1.
In group one?
What's the name of the group 1 as a group, as a family?
Oh.
Family.
Wait,
Wait, like
which
lithium,
group
sodium,
one?
potassium,
Mhm.
alkali metals.
Alkali metals. Why do we all call? Why are they alkali metals? Why are they all in the same family?
Because they're
They all are in the S block. No.
Well, they all are in the S block, but why do we? I mean,
Because
first,
they only have one electron in that block, because they wanna get rid of it.
yes, but why are they a family together?
Because they like each other.
Because they share properties.
Because they share properties,
Because they're all
right? We knew properties first. They all share properties.
There's a lot that goes into defining this.
Well, why do they share properties? Because they all start filling S.
Yes.
So they have that electron in the same position, just farther away from the nucleus. Okay. What do we call the last group, the helium group? What do we call the
Noble
helium group?
gases.
Noble gases. And why are they all in the same family?
Because they have the same
They're
properties.
all
Because they have the same properties. Well, when we fill all the way across, once we get to the noble gases, can we put any more electrons in that principal number?
No.
No.
So you have to go to the next.
So we gotta, okay. So they have similar properties because the structure of their electron cloud
It's relative
is the same, is, I don't wanna say the same,
moderately.
is
Unique, similar.
similar.
Oh, it's figuring out this.
Alright, so, that's kind of where I wanna stop. So, we get there. So Friday I'm gonna give you your assessment review.
I'm in on Tuesday.
So I'll give you some time to work on that.
What's it on?
Either 1 or 2 days. 'cause then
You can't do it anymore.
I'll get, so the test is gonna be over Bohr model, quantum model, light. No, but you can't study. And you can use your periodic table.
Oh my God.
Yeah, on Friday, you gotta like.
Well, I'll give you the questions so you'll know what the assessment is.
So you can write it on the periodic table.
Oh, so the questions you'll give us are the questions you're gonna give us from the test. When is the test?
Next week.
Oh, I thought it was this Friday.
Oh, God, no.
Oh, jeez.
It's a wrap.
No, I'm giving you the review on it.
With snow. I'm still going with it.
The molecular formula of the water molecule is not.
And you know, think about solid liquid gases. Yes. Gas, the molecules are arranged.
Everywhere.
But then in a liquid, they condense enough to hold closer together in this liquid, so that they still have a definite shape. But then when they solidify the shape, then they take on a shape.
I think I should be able to work. I don't like driving at night in this weather. I can't even see normally in the dark, so I'm gonna crash.
You know, most people can't see.
Okay, when I'm driving with my brights on, I still have a hard time seeing.
Mine is too. It's like on my LED lights, I can see anything.
Yeah, I know, you almost turned it
I did almost hit that deer. I've almost hit deer multiple times, but I'm just.
I've almost hit an elk.